Bonjour à toutes et à tous. Je vais faire une petite introduction en français pour juste lancer le séminaire. Je vais switcher en anglais parce qu'on a une audience plutôt internationale aujourd'hui, notamment avec le Centre d'excellence cyber japonais, qui nous fait le plaisir d'assister à ce séminaire. Donc, ils sont présentiels, vous les voyez pas. So I was just introducing the fact that I will speak in English to introduce Professor Raphaël Franck from the University of Luxembourg. I have my notes to not forget a lot of things, interesting things that Professor is undertaking at the University of Luxembourg. So Professor is a senior researcher, scientist, and entrepreneur at the Interdisciplinary Center for Security, Reliability, and Trust from the University of Luxembourg. He's the head of UBIX Research Group, which conducted research on distributed artificial intelligence in various disciplines and applications. Since 2023, he is also a member of the University of Luxembourg Council and adjunct professor at HEC Liège, HEC Liège. And since 2024, he's also the director of the IPBG Atlas Industrial PhD program. So without further ado, I'd be happy to hand the floor to Professor for his interesting presentation. Welcome again, Professor.
Thank you very much, Reda. Bonjour à tous. Konnichiwa. That's about my vocabulary in Japanese. I have to apologize. But it's good that the presentation will be in English, because also for me, if I would have to give it in French, would probably miss the technical vocabulary. Okay, so let's get started. I have, let's say, presentations for about 40 minutes, and then if there are questions afterwards, we can have a discussion. Before I get to the topic of infrastructure-assisted cooperative and distributed perception strategies, I will briefly introduce my group. Reda already did so I will not spend a lot of time on that. But just maybe a few more details. So we are an interdisciplinary research group at the Research Center of the University of Luxembourg. And the role is a little bit like also with SystemX. We like to collaborate a lot with companies. We work on European project, nationally funded project, and industrial programs. And let's say my application area is around connected and autonomous mobility, and that is also the topic of today. I have another topic in the group that is more recent, which is about data-driven energy systems. And the group actually also manages two labs, the 360 lab and the energy lab. The topic of today is more, as I said, on the mobility topic out of the 360 lab. And maybe I can briefly introduce the 360 lab. 360 lab is basically an hardware platform where we can conduct different research projects. The most commonly used is a car. It's a Kia Soul electric vehicle that we completely modified to do autonomous driving tests with it. We added a drive-by-wire system, we added the perception systems, we added the localization and the compute systems, and we developed our own software around it that is called Robocar. It's an open source project that you can download. We welcome academic and also industrial collaboration on the project. It allows actually smaller teams to really build their own self-driving car, because this setup has been designed in a way that it's actually not too costly. In addition, we also have a few driving simulators. One project that we do there is also teleoperated driving. How can we efficiently drive a car remotely using state-of-the-art 5G networks? This gets increasingly important now that the safety operators in the vehicles, in the autonomous vehicles, will be, taken out and replaced by remote operators. So that's actually a research project where we have quite a few industrial partners that are interested in those results. But that's not what we're going to talk about today. What I'm going to talk about today is is a project of one of my PhD student that recently finished about how can we deal with the perception data of autonomous vehicle, and deal in two senses is how can we use the communication infrastructure to offload perception data and process it at various locations in the network, on the edge or on the cloud, and also what techniques can we use to efficiently transfer this data, meaning how can we compress it in a way that we still keep a good accuracy but can lower the latency because we have to send less data. Here is just in two videos. This is our teleoperated demo that we did for to make the vehicle using 5G standalone network. Driving. How would you start? Okay, so now let's get back to the main topic of today, perception, and how we can use the network and different AI techniques to make perception more efficient in terms of lower latency and better accuracy. So this is an introductory slide. I won't spend too much time here. I mean, we all know that these self-driving cars generate lots of data, and the lots of data they produce come actually from the perception systems, right? The high-resolution cameras generate a lot of data due to the high resolution. They have the different color channels. Then you also have LiDAR data that generate point clouds, where we have millions of points that describe the 3D environment around the vehicle. We can have radar and so on and so forth. So just having a car that has multiple cameras, LiDARs, and if you consider this data completely uncompressed, raw, that's a huge amount of data to process. And often you need to have the information that is contained in the raw data in order to make the perception system behaving quite efficiently. So here we need to see how can the data be processed quickly and accurately to operate safely. And this is what I just said. If we have a look, for example, at the megabits per second that are needed in order to transmit, for example, this is one LiDAR. Here would be one full HD camera. Here would be 64 channels LiDAR, and here we would have 6 full HD cameras. And if we consider this uncompressed, raw, okay, and just would like to transmit that over a network, and if we look at what are standard speeds of 4G networks in urban environments today and standard speeds of 5G networks, we quickly see that we reach the limit, okay, of those networks. So the idea here is to see, okay, what can we do in order to reduce the amount of information if we need to offload the data through the network. You will now maybe say that, well, process the data locally on the car. This is one solution, but this requires to have a very expensive computing hardware on the cars or on the robots, and often this is not economically viable. Okay, so using the network to offload and do the processing of this perception data somewhere else makes sense, and there are different applications, and we will see some. Here we see the case of just a regular perception, a camera perception, where we detect using plain vanilla AI detector the different vehicles, traffic lights, pedestrians, using a compression on the image. Here is no compression at all. And then we have a compression factor that we add to the images that we gradually increase. And we see if we compress the images, and in the images, when we compress it, the image gets blurrier. Obviously, our AI detection will not work the same way, meaning that we won't detect the different agents around us. And if we look at here, for example, where our ground truth actually is 4 traffic lights, 2 vehicles, and 7 pedestrians, which we detect well when there's no compression, but where we almost detect nothing when there is a compression, that even for humans, you would even be able to recognize the different agents. But the problem is that the AI systems have trouble with it. So you cannot overcompress, right? So compression is one way to deal with it, but if you overcompress, then your application is simply not working anymore. So the main research question this PhD addressed was where to process the data to meet the quality of service of the application. And there we have, this is quite classic, so the onboard computing, so the local computing, that's, let's say, the standard way of still doing it. There's also the way to process this perception data on the edge of the network, so rather close to the car, in order to try to minimize the latency, or on a cloud computing infrastructure. And the more you go up, the bigger your compute, basically. Locally, you might just be able to run small AI models on the edge, medium, and when you go to cloud, basically, you have all the resources needed. In this talk, we're going to talk more about the cloud and the onboard computing. And the second main research question is, what compression techniques can be used to reduce the perception data size without impacting the detection accuracy? Okay, so what we already said, there are different ways to compress. The one we saw before, we compress an image, right? We have an image from the camera, we compress it, we send it over a network, we do some process. Another way is not only to consider the image per image, but to consider a video, a flow of video, which has several advantages because you have this time component where you can, in addition, add some compression on top. And that is something we're going to talk about more in this talk, is neural network quantization. Okay, so we have a deep neural network. And this deep neural network have different layers, right, where we pass the data through. And the idea is that we cut the network at some point, and we do some part of the processing locally, and the other part of the processing on the cloud. This is kind of a way to compress. It has several advantages, maybe also some disadvantages that we will see. Yeah. So before we go into the detail, the PhD student started by seeing where can we actually evaluate cooperative perception, and the natural platform to go through is obviously simulation, right? Because you can just simulate different scenarios, and then already do some nice evaluation studies. However, it depends on which kind of simulator you're using. There are not a lot of simulators available even still today. This PhD started like 4 years ago, where you have everything all together, meaning a photorealistic environment, a very accurate communication channel, a very accurate traffic model. All of this there's no, to our knowledge, still today, a single framework that allows to do this effectively. Usually there are different frameworks that are put together in order to achieve it. Very popular simulators, Carla, for everything that is self-driving technologies and how they will be evaluated in a photorealistic environment. And everything that it has to do with, let's say, more traffic flow optimization that also integrates communication. There, Sumo is usually the go-to And there have been some attempts in the past now to connect these two worlds so that we can have the simulation model for traffic, for the photorealistic environment, and also the networking side. We did a small study just to evaluate actually what is the impact of using, for example, a framework like Zumo when it comes to perception. Because Zumo is not a photorealistic environment. You have this very basic kind of graphical user interface where the cars are driving, not like Carla, where you have all the different the different lighting condition, but also the different weather condition, and on top of that you can run different AI models. So we just wanted to see what is actually the impact if you use such a simplistic approach like Zumo on the perception. Is it actually realistic? And because there have been a lot of studies that have used this, right? And I mean, the intuition tells us already that there might be a problem there. So we came up with a framework that tries to make a course simulation so that we can basically compare the same traffic scenarios that run in Sumo but also in Carla and see what the perception gives us, okay? And then evaluate the impact, for example, of different day times or weather conditions, right? And in Zumo, we use based on the paper that is quite well known, we use a grid-based approach. So if a vehicle is in a certain field of view in front of the ego vehicle, we consider that the vehicle sees this car. So you have a kind of a binary detector here. You either can see the vehicle because it's in your grid, or you cannot see it, it's outside. That's already a difference to what you can do in Carla, because there you have a more probabilistic view on things, because a car is detected at a certain probability, right? That's the first thing. Here we have one example of the ego vehicle that looks in Carla and sees all of the cars that are here, the ones that are in red and the ones that are in yellow. The ones that are in yellow are the ones that in a simulation like Zumo you won't be able to see, okay, using this simplistic approach. So that already tells us that if we run a perception evaluation on Zumo, we might miss actually a lot of vehicles, and this can have a quite big impact on the overall application. So here we see the difference. If we run this through the entire simulation, we see that the number of detected vehicles in difference is on average around 3. Okay, we missed 3. And here I'm considering a good weather condition, okay? But there might also want to look at different weather conditions, right? During the day, during the night, rain and fog. And obviously the difference is in foggy weather, you will be able to see less vehicle confidently, right? And if you look at the empirical cumulative distribution function of this actually, and you compare this to what Sumo sees, you see that Sumo is here kind of almost in the middle, actually close to what we see in the day, but as we saw before, we miss a few. But interestingly, in raining nights and foggy conditions, obviously we see even less. Okay, so that's interesting to see that Carla is on both sides, right? If depending on the weather conditions, we see less, and otherwise we might see even a little bit more. Meaning that in case we use such a simplistic simulation environment, we will most likely not be close to reality. Now, if we consider this in a cooperative way, and if we assume that these cars are connected and within range, okay, and here I'm talking to vehicle communication between the cars, and here we assume a range of 100 meters. So if a vehicle is within 100 meters of another connected vehicles, they are able to exchange data on what they perceive. Okay, and of course, if we have the connectivity, we quickly will see that this makes even a bigger difference, right? Because if we have all the connected vehicles that see less, and if this is exchanged, then the overall result in a scenario will be much less than in case we would have a perfect perception. And here's a little bit the results for scenarios where we would assume 30% of all the vehicles are connected cars, 40, 50, and 60. And we see that every time the number of detected vehicles with Zumo is largely underestimated, okay? Especially for vehicles that are less, where the penetration of connected vehicles is less. So this is basically just to give you a warning about cooperative perception, how to evaluate it, that you have to be careful if you use this more simplistic environment, because you might miss a lot of very important information, and the results actually that are presented might not be 100% accurate. So that was a little bit the warm up, okay? To now come to let's say more the last part of the PhD of the students. I choose the beginning and the end, okay? Because to show everything would be too much. And in his last work, which is entitled Cloud Assisted 360-degree 3D Perception for Autonomous Vehicles using V2X communication and hybrid communication, very long. There we wanted to evaluate, using some real data and some real network, communication network, how we can optimize the use of a neural network, a perception model, and cut it at different layers to do the perception partly locally and partly in the cloud. And by setting different kinds of compression parameters, clipping parameters, and quantization parameters, and see what this gives us. So you might have heard of the work BEV Former. It's quite known by now. There's also a second version of it. We based this work on the first version. It stands for Bird's Eye View Transformer. Okay, so it's a transformer architecture that takes as an input 6 cameras, makes some sensor fusion, is able then to create a bird's eye view out of this and basically see where the different vehicles are. And the cherry on the cake is it creates 3D bounding boxes even out of that, right? Without the need of a LiDAR. It uses a quite fancy neural network for this. We are not claiming here to have done anything on the neural network side. We just use the model as it is, and we try to basically cut it at this different location and see how this affects the distribution of the perception data. What we did at first was to see how much resources actually this uses if you run this on a quite typical local onboard, and this is already a GeForce GXT, which is a quite decent laptop where we assumed that this could be a good onboard computer, and how much resources this takes to run such a neural net. This is quite heavy, okay? This is really lots of camera data, quite a lot of pre-processing, so it takes a lot of resources. And this is only for the one perception task, okay? If you have to do other perception tasks or the planning or whatever, then you need quite a bit of resources. So we want to see, can we actually avoid to process everything locally? The research questions, or let's say the characteristics of our application here is that we want to have a real-time perception. For us, this would be to be able to process the environment 10 times per second, okay? 10 hertz. That's our kind of go-to. There are some papers that say you need to go higher, 20 hertz. It depends on the speed, obviously, right? How fast you want to go. We take now just 10 hertz as, let's say, our benchmark here. And can we offload the sensor data for cloud processing? Is it feasible using existing communication technologies with their limitation, their bandwidth, and so on and so forth? And what is the trade-off between the detection accuracy and the end-to-end delay? Because that's the big trade-off, right? You can compress so that you cannot see anything anymore. You would just transmit a couple of bits, but that's not really helping you, right? So the experimental setup, we call this an kind of a hybrid way of looking at it. The first is the just pure onboard computing. There's nothing special here, right? So we have this setup where we have the 6 cameras, where we use our BEZ former. We do our detection, and what we add, because we're still talking about cooperative perception here, what we add at the end is we disseminate what we detect to surrounding vehicles using V2X, and in this case, ITS G5, so the Wi-Fi kind of protocol for vehicular communications. And we use the cooperative perception message format. Okay? This has been standardized. We see what's around the vehicle, we put it into this message, and we disseminate. And that's basically where we measure then the entire end-to-end delay. From the moment we get the images, the processing, and the dissemination. And then we compare this to this hybrid computing here, where we have the first part, which is still the same. But then from our neural network, we do different steps in addition. We do our feature extraction, which would normally be done, by the model automatically. But here we actually intervene. We do a specific encoding. We do a specific compression. And then we use, in this case, we use CV2X. So we use a mobile network technology to send this feature vector to the cloud. In the cloud, we decompress it, we do the decoding, and basically by doing the decoding, we did the perception. And then we send back what we perceive to the vehicle, again, using the CV2X or the mobile network, okay? And the result should be the same. The advantage of CV2X is just that, well, you could disseminate this information everywhere, right? But it only makes sense to do it locally anyway. So as the cooperative perception, the advantage of is that the local vehicles exchange to get a better view of what is there. So we just assume that here the perception task is exactly the same. And we want to see what is the end-to-end delay and the accuracy. So we evaluate the real network. So all the network metrics that you see have been evaluated using real network. For the onboard computing, the first scenario, we have this ITS G5, where we transmit the data in this area. This is around the University of Luxembourg. It's on the area of Kirchberg in Luxembourg, and there we measured different exchanges of cooperative perception message and see what is basically the latency we can expect, okay? So that we can afterwards use this for our calculation. And for our hybrid scenario, we also have a larger route. This is basically also the route we use for our self-driving car to drive autonomously. And around that area, there's a lot of 4G or 5G base station. For now, it's almost only 5G stations on this 700 megahertz and the 3.6 gigahertz. Please note that we are never really stressing the network here to the maximum. So it's not really important to have a network technology that has a very, very high bandwidth. Here, really, the most important part is the latency of the network. And we are talking about a non-standalone network deployments that are commercial. Non-standalone means that this is 4G core, okay, still, right? So the delay is a bit higher. So in the test area, we have a download throughput of around 55 megabits per second for 4G and around 105 for 5G, and upload is between 20 and 30. throttled by the operator. Okay, so the hardware configuration here. So on board here we have a little bit another configuration as before. It's already a quite powerful onboard computer. It's a Jetson AGX Orin that can do 131 tera operations per second. It takes around 30 watts. It's limited in resource for real-time processing, but depending on how you configure it, it's already quite powerful. On the cloud, obviously there we can just go crazy, right? And we use actually the HPC of the University of Luxembourg here. And for this task, we reserved four NVIDIA Tesla V100, where we can go up to 500 teraflops with 3000 watt of power. And obviously we can do much more and much faster there. Right. Now, there is the steps that are really crucial here to do this optimization, and there are a few things to take into account. This is the algorithm, and if you're interested in really getting into detail, you can look at the paper. I will just give you this. This should be 2 and it should be 3. So these are the 3 important steps here. So one thing, in case you're a bit familiar with neural networks and features, feature extraction, and so on and so forth, you know that these features are basically vectors composed of numbers, right? And they can have different precisions, right? It can be floating point 32, can also be floating point 8, for example. And obviously, if you go down in precision, you save a lot of data, because you kind of compress. You lose a bit of information. Obviously, it's like removing, rounding up a number, because you lose everything that is behind the comma. But this is obviously a technique that is very important to use in order to compress and reduce the data. So setting a precision, we will test here in this case the 32, which is the standard, then 16, and then 8. Then the feature extraction, okay? Select the split point. So you have these different, the different layers in your neural network where you can do the cut. Take this feature vector out, setting the different precision, and then send it over. So that is one additional critical point. And then the vector clipping, and clipping can also serve as a way to bit further compress the data, because we remove extreme values, okay, out of these feature vectors. This has several advantages and quite standard way of denoising neural networks, removing extreme values. It's also more robust to different adversarial attacks. So this is a quite standard way to do it. But the interesting characteristic it has, that it also further reduces a bit the size, right? Because we remove these extreme values, and here we do that at the 10th and at the 19th percentile, to get our distribution a little bit more narrow. And then we have our feature vector of numbers, and we compress it, okay, using a zlib compressor, lossless, and send it over the network. Okay, so there are different things we can then try, different parameters we can set. What we use to evaluate this is, and that's also what has been used in the BEV former initial paper, is the new scenes data set that you may know. It's quite known data set in autonomous driving, because it also includes already the ground truth and everything. So we have a good a baseline. It has these images. It has six cameras, has 5 lidars. 5 radars, 1 lidar. We are going to use only the cameras here. It comes with a pre-trained model that we can use. So there's no specific training. We only run inference here. No training. And our evaluation focuses on the accuracy on the new scenes detection score, the NDS. That's the new scene detection score. That is a metric that has been defined by new scenes. I will not go into detail exactly about how this is now calculated. What is important is that it considers the mean average precision as one part of the score, and it also looks at another composite metric that looks at translation error, localization error, and a few more. Don't ask me them now by heart. I don't know, but there are 5. That's also why you have actually 5 times here, because it's equally weighted. So it looks at not only the mean average precision, but it takes into account those dynamic factors as well. And as a result, these new scene detection score is more realistic than just looking at a simple mean average precision. Similar to all of the other metrics, it ranges between 0 and 1, 0, nothing, 1, perfect. And we are looking, obviously, something in between here. About the results now. So this is now considering the onboard computing only. That's our baseline. Okay, we look at the baseline onboard computing. So the local inference takes a long time, more than half a second. Okay, and we get to a new scene score of 52%. This is not bad. It's not great. And it's not the ambition of this work to get a very high score, right? It's just to see how we compare to the baseline score, okay? If you look at, for example, the new BEV format, the baseline is already higher, right? But again, this is not the point of the paper. The point of the paper is to see how we compare to the baseline. So now you might know, in case you're a bit familiar with neural network, there is a way to optimize your model by using TensorRT, for example. If you use these optimization techniques by NVIDIA, you get actually down to less than half a second, 486, in a floating point 32, right? If we now compress using quantation to floating point 8, we get to less than 200 milliseconds. That's already quite an optimization, okay? And at the same time, and that's the interesting part, is that we almost lose nothing. We lose 1% by going down from a precision of 32-bit to 8. We only lose 1% in detection precision on the new scenes score, which is actually great. Then we also look at what is the average latency of sending a cooperative perception message, so the networking component. Here with a standard deviation of around 1.5 milliseconds, and then we get to our end-to-end delay, okay, which is not bad, okay. With floating point 8, we still higher than what we initially said. We want to go to 10 hertz, right? Doing it 10 times a second. If this would only be possible to do it 5 times per second with this computing hardware and those configuration using floating point 8. Okay, and here we have not talked about cutting yet and nothing. This is only looking at this locally. So that's our baseline. Here are the network parameters of the ITS V5 and the latency we measured in this loop I showed you before. You can see that on average we lie around 4 or 5 milliseconds. So the message is also a bit that the network doesn't really matter, right? It's the inference that is really inducing the delay. Good. Now we get to the interesting part. If we do the hybrid computing, meaning if we now take our neural network as we had it here, right? So we had this now evaluated, but now we're going to cut at the different layers and see what this gives us. If we send it then to the cloud, the processing there. So there are 2 things to consider here. One thing is feature extraction, okay? You need to extract the features from your neural network first. This takes a bit of processing. This is what you will do locally, right? And you can do that at different layers, okay? Here in this case, this is a graph that shows you how much time it takes for the feature extraction if you define different layers. So this is let's say, at the beginning of your neural network. This is at the end of your neural network, okay? So now we take here as an example, if, for example, we cut at layer 5, okay? Here we are already quite close to what we wanna go. What we have here is that our feature extraction in floating point 32 cost us 55 milliseconds in 1620, and in floating point 9 milliseconds. And the feature vector size, okay, so the pure size of our vector, if we look at this in megabits, because that are quite heavy vectors, we're talking about 42 megabits for FP32, 31 megabits for FP16, and 23 for floating point 8. So if you now see, if you continue this, the extraction will go up, the time will go up, right? But all your feature size will go down. So you need to find the right trade-off here. So you need to find the right balance that works for the application. Right. So now some further results here, and what we use as communication here is just a simple UDP, okay, in order to try to optimize a bit further our latency. We just send the data. There's no retransmission, nothing, and we measure then at different split layers what is the translation latency for these different quantization here. And here you can see that actually the more you go down, obviously in the layers, the lower your overall transmission delay will be. This is quite classic. For 16 and for 8, it's also even further. So here you could see, okay, well, what we want is we will most likely like to cut here at the fifth layer and have a low quantization, because that will really lower our transmission delay. But we also need to see what impact that will have on our quality, right? So what we did in order to showcase this quite nicely in a graph is that we see the overall end-to-end delay versus the detection score. The 100 milliseconds is basically what we want to achieve, right? It's 10 hertz. So everything that is smaller than 100 milliseconds is good. And this is our baseline that we did locally, right? And you see in 52%. So we want to be as close as possible here, right? So the best trade-off would be in this case this one. Here we can see the split layers. That's in orange. This is split layer 2, and with a quantization of 16. Okay, which gives us still a much higher Newton detection score. So yes, with quantization 8, you go down in end-to-end delay, but you lose in accuracy. So you need to find the good trade-off. And here our best trade-off is FP16 at layer 2. And like this, we basically meet the application characteristics that we set. So these 10 hertz. There are some other, you can see other policies here, like for example this one, which is really a very low end-to-end delay, but the detection score is very bad. So we don't want that. If you want to see all of this all together and see also what are the different, these end-to-end latencies composed, obviously, of all of these different steps here. Knowing that you can see that what is the highest transmission latency, blah, 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 processing time backbone. And there's actually, no, forget what I said. So you have these different processing types that add up, okay? And here you have the end-to-end delay and the bandwidth that is used, and the different accuracies that are achieved on the NDS. So this clipping, compression, and network offload can significantly reduce this end-to-end delay and also the bandwidth utilization. And everything, if we consider our goal of 10 hertz, everything that is in that box would actually qualify, right? If our application would say we need to go close to even 20 hertz, which is not achieved here because we are still at 61, But this would still, I mean, there would be configuration where we could go faster, however, at the expense of the accuracy. Having said that, you can, of course, try to have more processing in the cloud, for example, that will get your delay even further down. So there might be configurations with different hardware where you can actually achieve this. I look at my watch. Getting to the conclusion, so I think I'm almost on time here. So what I wanted to show today is a little bit what different perception strategies exist. It's not only onboard, but we can also think of different strategies. There are different kind of robots that will most likely do the processing not on board, but somewhere else, on the edge or in the cloud. There are companies already now that offer this. They call it perception as a service. You offload your perception, you get it back over the network. They guarantee you a certain latency. So that's an active, still an active research, but also commercial area that starts to develop more and more. There are different techniques that can be used. Simple compression, being it image compression. Also video compression is interesting. I haven't showed it here, but video compression can also be used with different video codecs that are very efficient in compressing data and taking into account this temporal aspect to do so. And then there is everything that has to do with neural network optimization using different techniques like clipping, quantization, and then compression of the vector, the feature vector at these different split points in the network. Future work, there are some ideas that you could look at dynamic quantization techniques where you would based on a certain situation choose one or the other. Floating point precision, or also the investigation of heterogeneous networks to use multiple network technologies at once to even further distribute, let's say, the offloading and as such further reduce the delay. But this is the ongoing research ideas. With that, I thank you very much for your attention, and if you have questions, please feel free.
Thanks for the presentation. I'm wondering for which kind of application you are using the cooperative perception. Is it safety related? Is it because here the delay matters from the cloud to the vehicle, back to the vehicle, or back to the pedestrian. Here, the delay is very, very critical.
Yeah.
So.
Yeah, I haven't specifically discussed this. We just said we use this 10 Hertz as our starting point. So for low-speed application, 10 Hertz, 10 times a second, where you get the information about what is around you, typically in urban settings at speeds up to 50 kilometers an hour, you can then, calculate how many meters you drive until you get new data in, is typically secure enough. But you are right, this is not, this 10 Hertz should not be the one and only number. You need to look at this a bit more dynamically. So if you drive faster on a highway, for example, 10 Hertz might not be enough. And there you need to really guarantee a good perception.
The perception of information to a vehicle or to a road user, right?
Back to the vehicle. So at the moment where you start perceiving until you know what's around you.
Okay. And I have just to my.
Yeah.
Bird's view is like, bird's view of the road, of an intersection of a road. And so do you have other vehicle or infrastructure transmitting to the cloud perception, or I cannot connect both if you like. I did not understand it.
Yeah. Okay. So in this case, it's really only one vehicle that would perceive and would reconstruct this bird's eye view. Okay. This is typically done because it's kind of a sensor of fusion of different cameras that allows us to have this bird's eye view, but not only. We can create out of the bird's eye view 3D bounding boxes. And these 3D bounding boxes are afterwards evaluated on these new scenes score. Okay, so it looks at basically 3D. It's not only a pure 2D perception where we just look at the vehicle, but it reconstructs this 3D view. So the experimental stuff we did for the latency of the network. Okay, we did on the new scenes to run on this hardware that would be in the car. We run on the new scenes data set because then we can also compare to the ground truth. And we add the latency of a real network. That gives us actually most likely the real answer. Yes. Yeah. The vehicle in itself does not do the perception directly. We use the new scene data set to do that. But yeah, that's a good. I also always said to the student he should really explain this well. I probably didn't do it myself this time. Yeah, but we assume that that this is actually close to reality because the inference, everything has to do with neural network, and these delays can be done in the lab, right? You can calculate this if this is done on board of a vehicle or in the lab. It's simply we need to test the network latency and to get the real experimental network latency. That was important.
Yeah, we're doing applied realization also, so we need also to see operationalization of the concept.
Exactly. Yeah.
Francesca, you have a question?
I have another one speaking from.
I need to get close here.
Cannot off the speaker and then have the microphone.
Yeah, sorry. So yeah, please.
Okay.
I reduce the volume as much as I can. So my question is about what happens if you have several vehicles observing overlapping scenes. Maybe you didn't get to that yet, but intuition tells that you should be able to use this redundancy to reduce the amount of information that you get from each vehicle.
Yeah.
And this would require a shared network, like neural network between the vehicles and something at the cloud or the edge or whatever. And I was wondering whether it is something you looked at or that might be doable from your point of view.
Good point. Actually, the student now, although he finished his PhD, he submitted another paper to the Vehicular Networking Conference, the VNC, which is in Portugal soon, if you're interested to join. And he's exactly also looking at, okay, if you have multiple vehicles that do that and then disseminate these CPMs, how can you merge the CPMs? So no, we did not consider now that maybe multiple vehicles would share one neural network or something like that. We didn't consider that. The only thing that we would do is more on the post-processing side. Once one vehicle perceived and you send CPMs, that then obviously, with the look, you give an estimate of the position of this vehicle that you sensed, right? And then if you have multiple CPMs, you can see which ones are the ones that both vehicle that would merge them detect. That gives us an idea then of who sees what. Yeah. Yeah, that's a good question. Yeah, we had one paper actually on video compression completely. We did more or less the same graph as you saw there. I cannot really recall all the results by heart, but I can refer you to the paper. There is this H.264 codec that you can use. That you can set different compression factors. So there's two things. There is compression factor and there's the starting resolution that you use. And with the starting resolution also comes different neural networks that take different resolutions as inputs. And they are similar to this study. There are multiple parameters that you can tune. And then you get a result on what works best for you. But I cannot tell you now by heart. But I gladly refer you to that paper.
Maybe last question.
Issues perceptions. Say vehicle that sends bad perceptions or a little bit modified perception? Do you try to evaluate a little bit the impact on the precision of the model?
Yeah, it's a very good point. It's a very important point also, but the answer will be short. No, we didn't. Let's say there are some other experts that look always into that. The only thing I can tell you is that the clipping the clipping part helps against attacks. It's the only thing, because the neural networks are less perceptive to injection of these very extreme values. To basically falsify the detection. But more than that, I mean, there's certainly ways to make attacks on these kind of scenarios. So yeah, cannot tell you more, unfortunately.
No other questions? I have maybe one last question. It's a little bit aligned with the question of, and it's because we're working on cybersecurity and trustworthiness, so this is part of. I was wondering whether there is a kind of heterogeneity in the system, because you in the first part of your presentation you mentioned this connected, non-connected vehicles and the impact on the simulation and the veracity of the results. So. What happens if we have a completely heterogeneous park of vehicles that have different strategies? For instance, the split learning, as you said, it has an impact, and how we could detect what are badly performing and versus those that are maliciously injecting false perception.
Yeah, that's a very good point. I would see that as almost future work for us. Because that would take it really a step further, where we would have different actors that maybe use different techniques to do the perception, and then based on a certain redundancy, because there's overlaps in perception, and then see what could be. Oh yeah, there's this. I mean, there are very basic techniques like majority voting or whatever that could be used. There are probably some other techniques to validate, let's say, the scenario. Maybe you can even inspire yourself from blockchain techniques, or I don't know. But there also, unfortunately, I cannot give you a clear answer. But it's actually an interesting point that in case there are some of you that want to look for new research avenues, this could be interesting. Yes. Yes. Yeah. Yeah. I mean, there is a lot of work ongoing on explainable AI, where really you look at the network in more detail, and here, I mean, these splits at different layers could potentially be a starting point to look at different different ways the data is processed. But again, I'm not yet too much into that topic. But yeah, I mean, there are definitely some thoughts there. Yeah.
Maybe tool for collaboration.
Well, that sounds already like an interesting topic. Yes.
Okay. So without any other questions, thanks again, Professor.
Thank you.